How much energy is stored in a spring with a spring constant of 150 Newton meters when it is compressed 2 centimeters? So to solve this problem, we need to know that elastic potential energy is equal to half kx squared, where k is our spring constant, which is 150 Newton meters, and x is our displacement, which is our 2 centimeters. But we need to plug in meters because we have Newton meters here, so we have to convert this to meters. In order to convert, we move the decimal place 2 places to the left, so we have 0.02 meters. So since we have our spring constant and our displacement, we can plug into the equation. So we have half times 150 Newton meters times 0.02 meters, and that is squared. So if we follow our order of operations and first square our 0.02 and then multiply by our 150 and our half, you will end up with 0.03 joules as your answer. Number 45. A spring with a spring constant of 175 Newton meters has 20 joules of elastic potential energy stored in it. How much is it compressed? So again, we start off with our equation of elastic potential energy equals half kx squared. In this question, they're asking how much is it compressed, so we are going to be looking for what x is. So to get x by itself, first we're going to multiply by 2 to get rid of our half. So we'll have 2 times our elastic potential energy is equal to kx squared. And then we can divide by k. And then we will have 2 times our elastic potential energy divided by k equal to x squared. And last, we will square root both sides to get x by itself. So we will end up with x equals the square root of 2 times our elastic potential energy divided by k. Remember that there's also the other version of this equation, which would be x equals the square root of elastic potential energy divided by half k. And either equations are acceptable. However, the equation that I solved for first is the proper mathematical way to do it. When we then plug in our numbers to our equation, we'll have x equals the square root of 2 times your 20 joules divided by 175 Newton meters. And again, in simplifying, you need to make sure you're following your order of operations. So you'll do 2 times 20 divided by your 175, get the answer to that, and then take the square root, and you will come up with an answer of 0.47 meters. Number 46. A spring stores 96 joules of potential energy when it is stretched by 5 centimeters. What is the spring constant? Now, using our equation of EPE equals half kx squared, we are going to be looking for our spring constant, so we need to know what k is. And in order to get k by itself, we are again going to multiply by 2 to get rid of our half, and then we can divide by x squared. And we will end up with the equation of k equals 2 times our elastic potential energy divided by x squared. Again, you have the alternate version of this equation, which would be k equals your elastic potential energy divided by half x squared. And again, it's not wrong, but this is the proper mathematical way to do it. And then if we plug in our numbers, we'll have 2 times our 96 joules divided by our 0.05 meters. Again, it's centimeters, so we need to do the conversion. And that gets squared. And when we follow our order of operations and get our answer, we should get 76,800 Newton meters as our answer. And the last question, 47. A 0.2 kilogram mass attached to the end of a spring caused it to stretch 3 centimeters. What is the spring constant? What is the potential energy of the spring? So this is a two-part problem, and we first have to find what our spring constant, or K, is. And then after we find that, we can find our potential energy, or our EPE. So first to find K, we need to remember that Hooke's law is force equals Kx. So we can manipulate that and divide both sides by x, and we can have K equal your force divided by your x. And in this case, our force is going to be mg because they provide us with a mass, and then our x is the value that it stretched. So we're going to plug in 0.2 kilograms times 9.8 meters per second squared, which is our gravity on Earth, and divide that by 0.03 meters. Again, they give you the value in centimeters and you need to convert. And when we do this, we will get 1.96 newtons divided by your 0.03 meters to get a spring constant of 65.3 Newton meters. So having your spring constant, or K, is the first part of the problem. And then the second part of the problem is finding your elastic potential energy. So again, that is half kx squared. So now that we have our K, we're using the same distance, or x, that from the first part of the problem. So we have half times our answer, which was 65.3 Newton meters, times our x value of 0.3 meters, and that's squared. And when we plug everything in, we will get an answer of 0.029 joules for our elastic potential energy.